Alright, so let's do an example on the 2x2 matrix that's not diagonalizable. So let's consider a differential equation. X prime equals to 3, negative 1, 1, 1 times x. So let's call this thing A. So first, our goal is to try to diagonalize A. So first we solve the characteristic equation, which is determinant of A minus lambda I equal to 0, which means 3 minus lambda, negative 1, 1 minus lambda equal to 0. This gives you 3 minus lambda times 1 minus lambda equal to minus 1 times 1 equal to 0. So 3 minus 4 lambda plus lambda squared plus 1 equal to 0. So lambda squared minus 4 lambda plus 4 equal to 0. So lambda minus 2 squared equal to 0. So the eigenvalue is 2. So we have one eigenvalue. And the multiplicity is 2. Alright, so after solving for eigenvalue, let's get to the eigenvector. So we solve A minus 2i times v equal to 0, which gives you 1, negative 1, 1, negative 1 times v equal to 0. So we only have one solution. It's called v1, which is 1, 1. So only one eigenvector. So because we have an eigenvalue with multiplicity 2, with the only one associated eigenvector, we know lambda equal to 2 is defective. And the defect, d, is equal to the multiplicity, which is 2, minus the number of eigenvector, which is 1. So it's 1. So the defect is 1. So we can refer to a chain of generalized eigenvalues. So the diagram of chain of generalized eigenvalues looks like this. So we have our v1, which is equal to 1, 1. We multiply by a minus 2i. This gets you 0. So to find v2, we need to solve a minus 2i times v2 equal to v1. So v2 will be a generalized eigenvector. Okay, so we solve a minus 2i times v equals to v1, which is 1, 1. So we're solving 1, negative 1, 1, negative 1 times v equal to 1, 1. There are a bunch of solutions. Any of them is fine. So this tells you that v1, this tells you that the first coordinate minus the second coordinate equal to 1. The second row tells you the same thing. So easiest, we can just pick the second one being 0 and the first one being 1. So v2 equals to 1, 0 is the solution. Okay. So I have one eigenvector and one generalized eigenvector pointing to it. So A has the Jordan form, P, J, P inverse. P is the matrix with columns being v1 and v2. So first column is v1, second column is v2. And J is almost a diagonal matrix. So the diagonals are the eigenvalue, which is 2. But we have a 1 here to indicate that AB2 is v1 plus 2v2. So this term gives you this 1. So this is a Jordan normal form of A. Okay. So according to the previous video, we know that the solution is x equals to c1 times e to the lambda t, which is 2t, times v1 plus c2 times in parentheses e to the 2t, e to the 2t, and in parentheses v2 plus tv1. So this is the general solution. And if you really want to write it out, then this is equal to c1 times e to the 2t. v1 is 1, 1 plus c2 e to the 2t. v2 is 1, 0. tv1, v1 is 1, 1. So the final solution is x1 equals to c1 times e to the 2t plus c2 times e to the 2t times 1 plus t. And x2 equals to c1 times e to the 2t plus c2 e to the 2t times t. So this is the general solution in scalar form.